That is one stroke without return. One means from this side to the other, from NTU to military college, then the other one to Flight 9, the final one to China. No way return. That's it. Okay, I don't think you guys have any kind of gossip. Anyway, I don't think you have any problem with this. Just do it by yourself. But I have a better recommendation for you. I told you already. If you split it into halves, right? Then do the layout for the first, then reverse layout for the second. You will compose the common centroid layout, but only for first order. Okay? That is the first. The second is what? Just like this. Divided by 2, you have 1, 1, 2, right? The larger one first. The largest one first. Why? Because the larger the transistor means much more insensitive to process variation according to Pilgrim's model. Got it? 越大的电晶体越开始越早做因为他们因为 Pilgrim's model 他们对那个制程变异比较不敏感。Okay, that's it. So that's it for the second recommendation. And what is the third recommendation? According to MediaTek, for critical devices, they hope we can achieve the layout for second order common centroid. How to make it? Similarly, you divide all those by 4, right? So do it for the 50%, 25%, then reverse it for the other 25, right? Then that is the fourth segment. You do the second segment with the reverse order. That's it. Okay? What I'm talking about? All right. Allow me to show you this again. If you have 4, 4, 8, right? Divided by 2, you get 2, 2, 4, right? Divided by another 2, you get 1, 1, 2, right? So for the first quarter, the largest first. So you have 1, 2, 1, 1, right? And how about the second quarter? Reverse the layout. 2, 2, 3, 4. Okay, 50% only, right? And how about the other 50%? How about the rest 2 quarters? Do it with reverse order. Congratulations, that's it. Got it? Anybody? Has any problem? No, right? Very simple. So you can make it for the third order, for the fourth order, but anyway, my recommendation stops here because even for the best IC design house in Taiwan, they only require second order common centroid layout. So I think my 3 recommendations will be good enough for you to not only survive in the future, but live happily since after. Okay? Let's go further because right now we have only partial of the circuit. Allow me to show you a complete circuit just like this. Can we stack the layout for it? The answer is yes, but also no. Because don't expect you can stack the layout for all of them all together. Sorry, I told you, apple with apple, right? Orange with orange. You cannot integrate the layout, stack the layout for apple and orange. No. Okay? So what you need to do is group the transistors to be stacked. For example, the most important one is differential pair, M1 and M2. Then maybe the second important one, M3 and M4, but they are all PMOS, right? So if you would like to simplify the overall layout, M3, M4, and M6. Okay, and finally, not so important one, bias circuit, M5 and M7. Okay, MOS here, MOS here, and PMOS there. However, to stack the layout for all of them, for all those three groups, we need to fine-tune the width. I told you we don't care about the length, but to stack all of them just like this one, right? All the fingers needs to have the same width in this direction, length there. Different length is okay, but different width never be okay. All right. So we need to fine tune as the IC designers. You have the right to fine tune your aspect ratio, for example, here and there, right? To make the overall pattern easier to be stacked for layout. All right? So let's go further. What we can do? Yeah, just like this. Because 60 plus 60 overall 120, right? So you can see 40, 72, very close to 120, so we make it 80. And how about this? 30, 30, and then, so very close to 180. Okay? Right? So we change it to 120. That's it. That's it. All right, and then that is the, allow me to show you the final result. That is our expectation. Totally, we have 3 stacks. 我们有3叠. All right, and we hope what? We hope to have close to square, or at least close to rectangular layout. So it means what? For each stack, 1, 2, and 3, we hope what? The same number of fingers. If you have the same number of fingers, then from the left to the right, they will occupy about the same area to make the overall layout as close to square or rectangle as possible. That's it. Okay? 为了让他们的那个布局比较方正，我们希望每一叠的宽度都一样，就表示它的折数、它的 fingers 的个数，希望要一模一样。Okay, that's it. So it means what? How many fingers per stack? 每一折要有多少根呢？要把它叠在一起。Yeah. So K is the number of fingers per stack, right? Right. So we need to find the common divisor or common factor. 你要去找到公因数。Maybe the greatest or highest, maybe or not, as you like. I don't care. Alright, but at least you need to find K means the common divisor or common factor. 公因数. That's it. So for example, 12. Okay, K equals 12. So for each stack, you have 12 fingers. You have 12 fingers. So for 12, it means what? This is 80, that is 120, right? For this one, you have 4 plus 8. It means what? The width for each finger is 10. Okay? And how about this one? The same. And how about that one? Sorry for that. You have totally 120, 120, and here 180. Right? So 50% more in width. So it got 15 for each. So you can see 10, 10, and this is 15. Which one is wider? or longer for your poly gate. Okay? Got it? In this way, we can integrate, we can stack the layout for all of them as close to a square or a rectangle. Very good. Do you get the point? Hopefully. Okay. Piece of cake. You are graduates. You learn all the background already. Supposed to be. Okay. In this way, let's go further. That is what I would like to show. But by small or little modification, you need to make sure nothing wrong with the performance. Sorry, this is 120. Okay, after simulation, oh, it's good. Then let's go further. Okay. Right now, I have only the number of fingers in each stack for you. 4 plus 8, 6 plus 6, and 2, 2, 8. All right. Allow me to show you the most important one, M1 and M2. That is the differential pair. You need to try your very best to get common centroid layout. Otherwise, you need to face a lot of input offset voltage. That is really bad for op-amp. Okay? That is the most important feature for op-amp design, to reduce the VOS as small as possible. So 6 plus 6. How to make the common centroid layout for them? I told you already. Divide by 2. If only for first order common centroid layout, we can get, right, 3 plus 3 for the first half. Then do reverse layout pattern for the second half. That's it. But how to make it? Okay, allow me to show you. You may say, hey, look, it's so simple. 1, 2, 3. Then 1, 2, 3. Right? Then reverse 6, 4, 5, 6. Then 4, 5, 6. Bingo, that's it. But the final pattern just look like what? 3 M1, 6 M2, and finally the other 3 M1. Yes, they have common centroid in the middle, I admit, but according to dispersion, they have almost zero dispersion. You don't mix them up, right? So we can make the layout even better than this. But how to make it? All right, let's redo the one stroke drawing for M1 and M2. Okay, let's go. 1, right? Don't go back. If you go back, 2 and 3, finished. Nothing more. Sorry for that. Be brave. Go further. Okay, so allow me to redo it. 1, then 1, 2, right? Then 2, 3. Finally 3. Oh, congratulations. That is for the first half. Then do it by yourself for the other half. For the second half, reverse the order. That's it. Okay? Then you generate something like this. Got it? We have not only common centroid, but also much better dispersion. Okay? Alright, let's go further. And how about 4 and 8? Oh, piece of cake, do it by yourself. Right now, allow me to focus on this. Because for differential amplifier, the most important ones is differential pair, M1 and M2. And the second important one actually is the load, active load, M3 and M4. All those contribute to VOS. Alright? So you had better have some kind of common centroid layout for M3 and M4. Okay, right now we have 2 to 8 For common centroid layout, what is my first recommendation? Divide it by 2, right? So you get 114. And then the largest first, right? Do it. Just do it by yourself. So allow me to show you this. The original one, just like what happened here. Okay? Oh, it is not recommended by me. I just Googled online and downloaded the slides for you. Okay? These slides were not made by myself, but who made it? Don't ask me, I forgot. Okay? But I was the first in Taiwan to teach one-stroke drawing for layout, for stacked layout. After I taught the engineers in Hsinchu, some of them taught the other professors. So till now, many of the professors, according to layout, they teach students the same idea. But I was the first because I Googled online the first. Okay. Yeah. Anyhow. How about 114? How to make it for the first half? Oh, piece of cake. You can do something like this. 1, 2, 3, 4. Don't choose the wrong node. Okay. If you start from here, sorry for that. You will end here and no connection with M3 and M4. So choose the correct one. We have 1, 2, 3, 4. Then 1. Oh, sorry for that. Right? Nothing you can do for the other one. So for this one, allow me to show you the idea. Okay? To complete it. 1, 2, 3, 4. Then 1, 2. Then 1, 2. Then 5, 6, 7, 8. That is what I have this for you from the original slide. But what is the problem? Yeah, we stack the layout for all those 3 transistors, right? But the problem is M3, M4, they don't have any kind of common centroid for layout. It means you need to face some VOS after fabrication. Alright? If you are not happy with this, okay, my first recommendation is to apply some of the dummy segment. Dummy means what? It is not functional for the real circuit. That is, you need to shut it up. In the past, dummy for what? To protect the main device during fabrication, right? But now, dummy is not for that kind of purpose. Dummy is for you to stack all of them at the same time to achieve the other good purposes, just like common centroid, blah, blah, blah. Okay? Yeah. And more likely also reduce the overall area. Maybe. Okay, and forget about it. Yeah. Just think this. You would like to stack all of them, but also with common centroid, it is impossible for this case. Okay, I show you already, right? Who? 1, 2, 3, 4. Then 1, no 2, right? If you would like to do the layout for the 50%, for the first half, wow, we stop there because we are here. We cannot go back. So what you can do? Dummy segment to help you go back. Got it? So the useless dummy, again, keep this in mind. Oh, sorry. Oh. Look. Pay attention to this. 1, 2, 3, 4. Right? Then 1. How to go further? Dummy. Got it? So please, this dummy finger cannot be functional for your real circuit. So after layout, you need to shut it down, shut it up. Okay, got it? Then the other one, bingo, right? You finish the first half, and then go back 2. All right, and then the same dummy 2, 5, 6, 7, 8. Bingo. So you will have something very similar to this, but this one is even better. Allow me to reword the procedure for you. 1, 2, 3, 4. Then dummy here. Got it? Then 1 and 1. For the second 50%, 2 and 2. Dummy back. Then 5, 6, 7, 8. You get this. Even better. Why? Because for the first one, M4 is here, then dummy 3, 3, dummy 4. Right? Compared to the original one, this one achieve more compact layout. We have common centroid, and then symmetry, and then compactness, and then dispersion, blah blah blah. Right? So according to compactness, this one is better than that. Because M3, M4, they are closer in the layout. Got it? Bingo! That's it. That is what I can help. I told you all the recommendation for one-stroke drawing already. Keep all those details in your own mind or write them down. Okay? 我甲所有秘密都甲你讲了，无写伫顶管，惊别人学去恁家己甲抄起来。Okay, that's it. That's it. But remember, to both sides, you need to have also dummy, and these are traditional dummy layout to protect overetching at the boundary condition. Okay, that's it. Do it by yourself. Yeah. Anyway, anyhow, let's go further. Maybe this is for homework one. I will discuss with TAs to make it or not. So after that, you have the stick diagram. We call it stick, right? 一根的棒子. But that is not any kind of real layout. I mentioned already, you need to be your own compaction program. According to the stick diagram, then finally do the real layout by yourself. Okay, yeah, from stick to layout. You know where are the polygate, where are the VDD, where are the ground, the orientation, the relative positions, blah blah blah. With stick diagram, we can control what you want for the final layout. Okay? But you don't need to do it by yourself because you have layout engineer in analog domain or you have EDA tools in digital domain. You don't need to make it by yourself. You simply have such kind of stick diagram to show them, I mean layout engineers or EDA tools, what you want. That's it. Okay? And hopefully with your stick diagram, the final layout will generate better result after fabrication. This is the second example. Again, do it by yourself. Yeah, you are smart guys. I hope you learn all the good ideas from myself. Moments ago, I told you all those recommendations. Keep all those in your own mind. Then you can make it by yourself. Yeah. Anyway. Yeah. Anyway, after some kind of modification, you have such kind of final pattern. But I will only like to tell you that X for M11, O for M10. That's it. Okay. Yeah. So, roughly speaking, I told you all the procedures to stack the layouts for a complete circuit. Right? I told you all the secrets. Yeah. Again, speaking is much easier to understand than reading. Okay? You read it by yourself, but I told you all the secrets already. Let's go further. On this page, I would like to share some of the secrets from maybe the most famous guy on earth for analog IC design, Professor Razavi. All right. And this slide actually was from Professor Razavi's textbook. Anyhow, Professor Razavi would like to tell you some of the secrets about layout. Unluckily or sadly enough, his life is black and white. My life is colorful, right? Anyway, our layout pattern actually are quite colorful. Yeah, better to read, better to see. But for Professor Razavi, he simply don't care. Black and white, good enough. All right. Anyway, anyhow, he would like to share the idea with you. You can see, for example, that is the so-called cascade structure, right? M1 for current control and M2 for cascade to increase the output resistance very much, blah, blah, blah. However, you can see where you need to connect the nodes. This is for input, that is for ground. Okay, that is for bias, and this is for voltage output, for your VO. And how about this one? Nobody needs to connect this node. Got it? It is useless for connection. But you guys are so lucky. I mentioned already, you have the so-called P cell. Right? So more than often, for you guys, if they are with the same size, they can be stacked. Just like, right? I told you, 1, 1. Ooh. Then you will have M equals 2. Automatically, they will help you. The EDA tool will help you to generate some pattern like this. Okay? But I told you already, this one, without any need to be connected, is useless, totally useless. Okay? So hopefully you know this, then remove it. If you remove, because no connection at all. Yeah, you guys with P cell, automatically you will get something like this. But you can make it even better by yourself. Okay? Please flatten. You need to flatten the layout. Then remove the portion you dislike, you don't need, and make it even more compact than before. Got it? You remove it, then it means the polygate of M1 and M2 can come closer according to design rule. Alright? In this way, you not only save the money for your boss, for your professor, but also you reduce what? Parasitic for this area. Got it? You can save money at the same time enhance the performance. Why not? That's it. Okay, if M1 and M2 are huge transistors, I mean the W is very much. So what you can do? 1, 1, 2, 2. Right? Just like this. Come on, centroid. Okay? And then, again, remove in the middle for the internal node. No need for connection. That's it. That is what Professor Razavi would like to share with you. How, in this case, in some cases, you can reduce the layout area and also reduce the parasitic capacitance. Why not? Alright, hopefully you get the good idea from him. And then, ring transistor. So, what is the idea I share with you? Usually it is no good for you. Okay? Unless the next device is far above it. Especially for RF circuit designer, inductor. It makes much sense. Except for such kind of very rare conditions. Please don't touch. Okay? It wouldn't provide you any kind of help. If you need for such kind of very wide transistor, later I will share some of the better layout patterns for you. Alright? Don't touch this again unless for maybe RF circuit, especially to drive inductor. Alright? Let's go further. I have better idea. Don't touch this. Okay? This. For the other kind of analog circuit, instead of RF circuit, this one is much better. Alright? We call it WA4 layout. Why? Okay, according to the layout like this, right? Let me show you the photo of WA4. Wow, they look almost the same. Okay? So we call it WA4 layout. 威化饼干。这样讲对吗？好像不太对。早餐店就有在卖这个松饼了，应该说松饼。Anyhow, what is the idea here? Actually, for each one, for each internal layout, the idea is quite similar to this. And what is the most important idea? You can see, look at me. I told you for the stack layout, source and drain. Then you flip it, source and drain. Then both sources can be stacked, overlapped. To reduce the area and the parasitic, roughly speaking, 50%. Right? So what is the function for such kind of square layout? You can see the same source and drain, right? The first, the second, the third, the fourth, all those actually overlapped in the middle. 4 overlapped in the middle. So it means what? 75% reduction in area and parasitic, but only for the middle one. Okay? For the overall layout area, I promise you, much higher than stacked layout. Okay? And this is another reason I told you don't touch. Not to touch such kind of layout unless you really know what you are doing. 除非你真的知道你在干嘛，不然你不要去碰这个家伙，因为它的总面积会变得非常的大。The overall layout area will much larger, not only than stack layout, even larger, I guess, than the original single finger. For example, if you have W equals 100 micron, you can do a single layout just like this. Okay? If you make it like that, 25 microns per side, oh gosh, you need to spend more than the square of 25 microns. I promise you, it will be much larger than this. Never mention about you stack some fingers of it together. Okay? Don't touch. But if you would like to reduce not only the layout area but also the parasitics, this is a much better way for you. Especially why we need such kind of very huge W over L. For what? very high driving capability. So the first application flashed into my mind is power electronics. For power electronics, yeah, you guys, right? You need to have power PMOS, power MOS. Wow. How much for this? To my memory, for usual application, maybe at this order. Wow. 10,000 microns. Don't do the layout for a single finger. It never make any kind of sense. Okay, too long. Even you can see the layout by your own eyes without the help of microscope. It doesn't make any sense, right? Right? So usually for power electronics designers, they have stack layout for that. Good enough, but you can make it even better with this to reduce the layout area and also parasitics. All right. Oh, I will have even better explanation for you. Again, for the middle one, I told you already, right? 4 in 1. So the area actually is divided by 4, roughly speaking. All right. If you are curious, hey, how about this? No worries. 1 and 2, right? So even for the corners, the worst case, it is divided by 2, roughly speaking. And how about this one? 1, 2, 3. Okay? So you can see in the middle, all roughly speaking divided by 4. To the corners divided by 2. Okay? And for all the others divided by 3. Alright? So the larger waffle means what? The area reduction were very close to 4. Okay? It's really powerful to save a lot of chip area for you guys. Hopefully you know what I mean. Okay? If you follow the layout pattern, your professors will be really, really happy because you reduce the layout area very, very much. Your supervisors or you even in the future your bosses don't need to pay a lot of money for that. Okay? Yeah. Maybe you will be curious. Oh, okay. Let me finish the pattern explanation for you. We wouldn't like to have any kind of overlap for your source and drain. So usually we would like to have such kind of diagonal wires for connection to connect your drain and sources. Okay? And you can see, they don't touch each other. It's a very good idea. Okay? And maybe you will be curious, hey, never mind who is the output. Never mind for source or drain, you have overlapped. You have overlapped, right? Yeah. But anyway, keep this in mind. You reduce the parasitics in the middle for at least 4 times. At least 2 times, at least 3 times. Okay, so maybe for parasitic capacitance, you don't make any advantage, but not so bad. Okay, that is my briefly explanation. However, according to the operation speed, it depends on R and C, right? Maybe C is not so good with such kind of layout, with metal one here, with metal one there. If you are curious, you can push it up for metal 2. Maybe you can think about this. Okay? Anyway, anyhow, maybe for C, not so good, but also not so bad. And how about R? You can reduce the resistance very, very much. Alright. Okay, allow me to show you this again. You can see how many fingers overlap altogether. 3 vertically, 3 horizontally, right? 3 and 3, right? So totally, I say roughly speaking, this is not any kind of accurate estimation, only rough estimation. Okay? So you have 3 fingers stacked vertically and the other 3 fingers stacked horizontally. So overall, again, roughly speaking, you divide your width by 6. 3 here and 3 there to be fully overlapped. Okay? In this way, how about the resistance for each finger? It is divided by 6 already. Rg for each finger. Okay? Then 3 connected in parallel, the other 3 in the other direction in parallel, and all those. Okay. And how much it is reduced? Again, my guess is it is reduced by this number, the square of your finger number. Okay? Wow! Got it? So it means what? For the overall RC of such kind of waffle layout, I promise you, you may not make any advantage for C. Maybe it is even worse, but not so bad, as I mentioned. However, you reduce the resistance for your polygate very, very, very much. In this way, I promise you, the operation speed for your power electronics is still much better than before. Okay? Got it? Hopefully, you get all the good ideas from myself. Yeah, waffle. If you love it, please keep waffle layout in your mind. Oh, this is what I told you already, right? How many times, roughly speaking, you can reduce the area, the parasitic, blah, blah, blah. Okay, the other lucky guys, I mean device engineers, yeah, they would like to know how much for the resistance, for the capacitance. Yeah, I have no idea from simulation or measurement again. But for comparison, they have 24 fingers stacked together, 48 stacked together, and finally compare with waffle layout. Okay? We have hollow ones to the left for R. 空心的看左边 solid one to the right for C. Okay? And which makes the minimum figure? Because R and C, we hope they are as small as possible, right? Okay, diamonds. And who are diamonds? Waffle layout. Got it? And then triangle, right? And then circle. So my guess is, again, the MOSFET is really white. All right. So you cut into 48 or 24. Actually, who is the circle? Okay, this one. All right. You were closer to square than the other. All right. But which is the real square layout? Waffle. See? That is our golden target. The final layout for the very critical, very important device. It looks like a square. That's it. All right? Okay. So not only for resistance, capacitance, waffle makes the best, but also for frequency. If again you look at the maximum frequency, yeah, who gets the best? Waffle, right? Here is for operation frequency. The star is better than triangle, than square. Yeah, here. This one the best. Then 48, then 22. Okay, and then compared to the how can I say? Anyway, nothing is free. You need to pay some price. And what is the price? This is a very good idea for you. See, according to variation, if we normalize the others with the worst case, you can see for waffle structure here, waffle versus 24 finger MOSFET, you can see almost 50% more in variation. Okay? And how about 48 versus 24? 10 something. 加10幾%，啊，迄個加比較50%。Nothing is free, you need to pay for it. But again, if you are power electronics guys, we simply don't care, right? Because you need the larger driving capability, the better, that's it. We don't pay attention. We don't pay too much attention to the variation. Only if it is large enough. And the area is small enough to save cost. That's it. Okay? That is what I can help. Yeah. And then, for digital guys, if they need such kind of wide transistor, in the past, usually they apply such kind of pattern according to EDA tools. They don't need to do it by themselves. EDA tools can help. Bent gate. Okay? That is the most famous one for digital wide transistor layout. And what is the definition for bent gate? You can see they are also stacked, but not with straight polygate. No, they try to bend the polygate regularly, periodically. You can see here, then, right? You can see here, up, then down, then up. It happens regularly. 规则性的把它弯上去又弯下来。So you can see 45 degrees up, then the other 45 degrees down. And how much the length here for bending and also for the straight knife, all of them are fixed. The length here, 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 and there, all of them are fixed. So according to such a kind of regularity, it is much easier for EDA tools to handle. But why we would like to have such kind of bending? Simply because with about the same layout area, we can achieve much longer polygate. It means much more W. Got it? That's it. Alright? But after this, we need to thank Professor 洪一教授的讲义。Very few of the slides actually went from Professor Huang. Okay? Then even better ideas is JUGM. Yeah. JUGM wide transistors also usually for digital one instead of analog. Alright. What is the definition for jogged? Just like you go jogging? Yeah, randomly, right? It happens randomly. So we try to break the regularity for bend gate. For bend gate, I told you how long and in which direction, 45 degrees, right? And how long? Everything is fixed. But we would try to break such kind of regularity. For example, how long for this segment? As you like. Alright? And then go up, how long? As you like. It means what? We get more freedom. The only restriction is still 45 degrees up and 45 degrees down. Okay? That is the only restriction. But how long here, how long there, no restriction at all. So we get more freedoms for layout. Just like, some of the good example after the layout done by EDA tools. With more freedom, it means we can squeeze more performance. We can reduce the layout area even more. You can see the only constraint is 45 degrees jogs. That's it. But according to length, Sorry for that. In the past, not only 45 degrees for jogs, but also the length for each segment are fixed, right? But right now, we remove the length for each segment. We totally remove it. With such kind of more freedom, we can get better performance. And in practice, after layout, the paper figure out that we can set more area by 20 something to 30 something. 还有送哈，去除长度的限制之后，我们可以节省20几%到30几%。But again, you need to pay the price. What kind of price? It is much harder to write such kind of EDA programs. Got it? You need talented guys in software. They can help. Yeah, maybe from computer science. They know all the algorithms to help. Okay? Their own business, not ours. Oh, yeah. Anyway, till now, we are all talking about very wide transistor. But for some case, we need very long transistor. How to make it? Oh, this is a good example. Not so good, but not so bad. Okay. You can see source here, drain there, right? And how about the carriers to move? Oh, they need to go all the and then finally touch drain, right? So the length is really long. Okay, and how about the width? Here, this is the width. That is the width. Okay, so in this way you can see, this one is very small, that one is very, very long. However, this is not my recommendation because, again, the W and the length is not so accurate. For example, the corners. Okay, the corners. Tell me how much W, how much L it is. Don't ask me, I have no idea. Alright? So, what is my recommendation? Some of the segments, okay, for each segment, drain here, source there, right? Then connect them by metal knife. That's it. So for each one, you have something like this, right? And your source and drain, right? For each finger, okay? Drain here, source there. So what is the length from here to there? Accurate, right? And what is the W here and there? Accurate. And many of them connected by metal line, this, and that. So overall speaking, it is also a serpentine. 它也是大蛇状的, but with much more accurate W and length. That is what I recommend you for very long transistor. Okay? In this way, you can do the layout very, very quick. And also you know how much you get for W and L. Okay? Yeah. Again, this is from Professor Hong Yi Huang's original lectures. But this is some kind of wrong example, right? It's so simple, 1 and 2. The differential pair, for example, and how to make the common centroid. I told you already, 50%, 1, 1, then 2, 2, right? You make this. But I leave this page for you by purpose because something wrong with the layout. Anybody? No. What's going wrong with the layout pattern here? It is drawn by Professor Huang's student, not himself. Okay, so don't put the blame on him. But this is a wrong example. You need to know what's going wrong, right? What's going wrong? Anybody? What's going wrong? The dummy. What is the golden rule for dummy? You need to keep the same spacing, right? You can see, wow, the dummy is here and there. the spacing is much more than the protected ones. It doesn't make any sense. Don't make the same silly mistake. Okay? Then we go further again from Professor Hong Yi-Huang's lecture. Yeah. Anyhow, I will only like to tell you how to do such kind of very good stacked layout with one stroke drawing. I show you all the detail here. So do it by your own fingers. Okay? So we can have a brief stop here. Yeah, just follow it. How can you make it to stack all the fingers for M's 1, 2, 3, 4 all together to make this one? All right? I help you to explain. All right.